Alright. So you can refer the slide from the Google Classroom, or you want to see from my screen. Okay. Semua siap ini?
Alhamdulillah sihat.
Alhamdulillah, sir.
Okay. Right. So yesterday we have learned about the characteristic of the lamina and turbulent, and we already know how to calculate the Reynolds number, which this Reynolds number will tell us whether the fluid is flowing with lamina or turbulent condition. And that's I hope you still remember that, okay, because this second chapter will related to the first one. You will need to know, you have to know how to calculate that Reynolds number in order to solve the losses in the pipe, because today we are going to learn about the losses in piping system. Okay, so basically there are two losses in a piping system. Ada two losses. I draw it for you. Okay, so one what we call as the major losses, okay, and the second one is minor losses. Okay, so this combination of these two losses will give you the total these two summation of these two losses will give you the total loss. Okay, the total loss in a piping system. Okay, so what is major loss and what is minor loss? So that's we are going to learn today. Okay, and how we can calculate that. Okay, the major loss is due to the friction, the friction of the pipe. Okay, so you have for example this diagram. So you have this pipe, panjang dia dalam, bagi sini 80 meter, 80 meter, and this 80 meter pipe will have a friction, and this friction will give you a loss, and that losses we call it as the major loss. So that's the first one, the first losses. The second losses, which is the minor losses, this is due to the fittings of this piping system. Okay, we piping system passes. Apa saja passes. Okay, so what is this? This is everything that you have in your piping system. For example, you have the entrance, you have the elbow, you have the valve. Okay, you have the if you have two different pipes with have two different sizes, and let's say you have one bigger pipe and then you connect with the smaller pipe. Okay, so you will have what we call as a contraction. This is a contraction, and opposite of that is expansion. If you have a smaller pipe and with connected with the bigger pipe, okay, so you will have this expansion losses. When this flowing from the smaller and goes to the bigger pipe, so you have another losses what we call as expansion. Okay, so this summation of minor losses for each of these entrance, the bands, the elbows, the teeth, the inlets, the valve, the expansion, contraction. So these all will give you the minor losses in your piping system. Okay, so we need to know how we can calculate that losses to give us the total losses in the piping system, and why we need to know that losses. Anyone? Want to guess? Kenapa kita kira losses ni? Untuk apa? Siapa nak try?
Kenapa kita kena kira losses?
Lah, why you calculate all these losses? For what reason?
Sebab nak tahu velocity sebenar
Nak tahu?
air tu. Velocity sebenar.
Okay, boleh. Dekat-dekat dah tu. But the main reason why we need to know that, we want to know what? Okay, if you have a losses, so what? Ada
Pressure air.
pressure air. Kenapa nak tahu pressure air tu? Okay, boleh dekat lah So we have discussed before in chapter 3, and we said that there is no in the Bernoulli equation that we use, we assume that there is no friction kan, there is no losses, and there is no mechanical device added in that system kan. But in chapter 4, because we know that there is a losses and we take that into consideration, so that's why we will put in piping system. Macam mana fluid ni flow? Siapa yang flowkan dia? Siapa how this fluid flow? Anyone?
Gravity.
Gravity itu kalau without losses lah, maksudnya dia just the gravity tu yang helps the flow through flow to the pipe. But in this one we have the losses, so that's why we have something that flow the fluid. And what is that?
Pressure.
Velocity pressure atmosphere.
Pressure. Daripada mana datang? Siapa yang provide?
Pressure. Atmospheric pressure.
No, it's just device.
Pump.
Yes, pump lah kan we introduction.
Pump.
Kita dah
Yes,
cakap
yes.
introduction hari tu. Mana? So any flow ni dia mestilah flow kan by fan or pump lah. Okay? So why we have the pump? Because we have the losses. So that's why we need to put a mechanical device to add to cover back these losses so that the fluid can flow fully inside the conduit lah, whether pipe or a duct. Okay, so that's why we calculate these losses. Okay, we want to know how much losses inside our piping system, and from there we can estimate what is the pumping power requirement for our pump to add to our piping system. Okay, so that is the main why we calculate the loss. So you need to know the reason why. Awak kira apa benda? That's the reason lah. Why we calculate that losses. Saya allow. Alright. So that's the reason. Okay, why we calculate the losses. Okay. So the friction cause the pressure drop. As you dah cakap tadi, ada pressure drop suatu kita kira losses ni, and that losses we can translate in a pumping power requirement. And for laminar flow, we have two different flow, laminar and turbulent. Okay, for laminar flow, you can calculate that pressure drop using this equation. Okay, the first equation. Okay, this is for laminar flow. So to calculate the pressure drop, P1 minus P2. Okay, another question. Why the pressure drop here, delta P is P1 over minus P2? Kan biasanya kalau kita jumpa, kalau you have a delta Y, the changes in Y or delta V, and the changes in velocity, normally you will write it as Y2 minus Y1 kan? Betul tak?
Betul.
The final minus the original kan? But why in this equation, the pressure drop, we write it as P1 minus P2. Why it's not P2 minus P1?
Sebab P2 lagi rendah dari P1.
Sebab apa tak dengar?
sebab itu lagi rendah dari P1.
Betul lah, right, that's right. Because we have the pressure drop, that's the term is pressure drop kan. So that means the pressure is reduced lah. The final pressure is reduced, is smaller compared to our original pressure kan, the P1. So that's why P1 minus P2 lah. Okay, so we already mentioned here pressure drop. Okay, so to calculate the pressure drop inside the laminar flow, you can just use this equation, 8 times mu times length of the pipe times the velocity, the average velocity of the flow, divided by the radius of the pipe, radius squared. Okay, and you can change this in terms of diameter because we know that the radius is d over 2. Okay, so r squared will be d squared over 4, and so that's why you have 32 here, 32 mu times L times velocity over diameter squared. Okay, so this is used only for laminar flow. Don't forget, it's only for laminar flow to calculate the pressure drop. Okay, you don't need to know how we derive this equation. Okay, that's beyond our scope. We can just use this equation. Okay, all right. So that's first. Secondly, in practice, okay, normally we can express this equation. We can use another equation for all laminar or turbulent or in a circular or in non-circular or smooth or rough surface. We can just use this equation. Okay, the pressure drop or the pressure loss. Okay, that's why they said here delta PL, pressure loss. For all types, regardless of this laminar or turbulent or the geometry, we can use this equation. So this is the most important equation lah. So this equation for laminar, turbulent tak boleh guna, but this equation you can use for laminar or turbulent as well. So that's why we can only just use this equation lah to calculate the pressure drop. Okay, and what is the equation? The equation is F, the friction factor or Darcy friction factor, ni bawah ni, okay, times the length of the pipe L over the diameter of the pipe times the rho, the density of the fluid, times velocity squared, the average velocity squared over 2. Okay, so this is the equation that we use to calculate the pressure loss. Okay, but we know that pressure pressure is equal to rho times G times H kan. And for pressure loss delta P, we can write this in terms of the head loss. Okay, H will equal to P over rho G kan. So that's why if you divide the pressure loss delta P L with rho G, we can calculate the head loss. The head H ni height kan. The head loss inside the piping system. Just divide the delta PL, the pressure loss, over rho G, and that's why you have this equation. You cancel out the rho, so you can divide by rho, and you times 2G lah. Ada G kat sini. Okay, that's the only difference lah. So that's why commonly when they ask you the losses, they ask you about the head loss. Okay, so that's just divide delta pressure loss divide by rho G lah, or we can just use this equation. Okay, to find the head loss. Okay, so that is because that's commonly used lah in term of the fluid flow. We calculate that losses, the column height in, can we know kan, kalau ada flow in a pipe and if we attach a piezometer, okay, this height will determine us lah the pressure inside this flow kan. And if you have the losses, and this height will drop to maybe here or here lah. Okay, so that's this what is called as the head loss. Okay, So we can calculate this head loss in meter. Head loss ni unit dia meter lah. Okay, the length the height that have been dropped due to the pressure loss. Okay, so that's why it's kind of related lah to each other. Pressure drop, and you can find the head loss, just divide the pressure drop by the rho g. Okay, alright. So the friction factor F ni, ini penting lah. This is the most crucial parameter, because yang lain ni semua awak boleh cari, awak boleh ataupun dibagi dalam soalan, the length of the pipe, the diameter of the pipe, the rho of the fluid, the velocity of the fluid, of the flow, and you can calculate the velocity. But this F, what is called Darcy friction factor, we need to determine that. Okay, we need to calculate that friction factor. Okay, because we use this F kan dalam equation ni kan. Ni pun ada F kan. Okay, to calculate that friction factor, dia ada dua cara. Okay, to calculate F, okay, ada dua cara, ada two method. This method will depends on your flow, whether it's a laminar or whether it's turbulent. Okay, for laminar flow, you can calculate the friction factor just simply using this equation, 64 over the Reynolds number. Okay, how we come up with this equation is just persamaan serentak between these two, between this delta P 32 mu L V over D squared equal dengan, we have another term for delta P is F L D ni kan. So F L over D times rho times V squared over 2. So to get F, okay, so you take out the F, you can cancel ni lah F boleh cancel, L apa lagi boleh cancel, D, 1D boleh cancel D, okay, and 2 you take you bring up to this position, so that's why you get 64. Okay, and you have mu, so you have mu. Oh, V pun you boleh cancel, V dengan 1V. Okay, and then you bring this term to the bottom position, so you have rho and 1D and 1V. Okay, so that's why you have this equation lah, 64 mu over rho dV, rho times diameter and times the velocity. And we know that the Reynolds number is equal to rho times D times V over mu kan. And this is just inverse of Reynolds number dah, mu over rho dV kan. So that's why you have, so 1 over Re sama dengan yang ni lah, mu over rho dV kan. So that's why you have the F will equal with 64 over Reynolds number. Okay, so that is for laminar flow. So laminar flow 64 over Reynolds number to get your F. But for turbulent, okay, we will use a chart. That's what we call as Moody chart. Okay, we will look after this. Okay, Moody chart. Okay, to get the friction factor. When we have this information, and when we have this value for F, okay, we can calculate the head loss inside the piping system. Okay, boleh follow sampai sekarang?
Boleh, sir.
Boleh Okay. So this we settle for this. Okay, to get your friction factor for laminar flow, just 64 over Re. For turbulent flow, we need to use a Moody chart. Okay, I will discuss this after in the next slide. Alright. And after we get the F, we can just plug in the value in our equation. Okay, kat sini. And with the same with the other value lah, the length of the pipe, the diameter of the pipe, the velocity of the fluid flow, and the gravity constant. So we can calculate the head loss of the piping system. Okay, but we make sure if the total head loss, jangan don't forget the total head loss is the summation of major and minor kan. Okay, major and minor, and the one that you calculate here, the head loss ni is just this part lah for that major loss. Okay, we still have one more, the minor losses, that we will discuss in the next slide. Okay, so when you know that the losses, okay, inside the piping system, you can calculate the required pumping power. The pumping power here, W dot is equal to the Q, the volume flow rate, and this volume flow rate, Q ingat continuity equation, volume flow rate, Q times A times V, okay, times the pressure loss, if you calculate the pressure loss, or we can change this pressure loss, okay, with the rho GHL, okay, because delta PL equal to rho GHL kan, okay, rho GHL. Okay, you can substitute this delta PL with rho GHL, and we can also substitute this rho Q with m dot, and we know the mass flow rate in your continuity equation is equal to rho times Q, and so this is why it's writing here m dot, because rho Q is equal to m dot, the mass flow rate. So mass flow rate times G times your head loss, you will get your pumping required pumping power in watt lah. Okay, in watt. Okay, how many watts that your pump will provide to cover back the losses. Okay, so that is how you calculate the required pumping power. So that's why we learn how we calculate the Reynolds number and the losses, because the Reynolds number is used to determine the losses, and when you get the losses, you will know what is the required pumping power. Okay, alright. So this is friction factor for laminar lah. But we still not yet see how we can calculate the friction factor for a turbulent flow. Okay, right, for turbulent flow, okay, we use basically this equation, okay, what we call as Colebrook equation. Colebrook ni nama researcher. He introduce this equation to calculate the friction factor for the turbulent flow. So this F ni, okay, you need to use this equation, and this equation is very long. Okay, so it's quite boleh je guna equation ni. You can substitute all the value that you have inside this equation, and you can find your friction factor. And in this equation you have this sigma over D, and this sigma over D is the relative roughness of the material. Okay, and to get this value, okay, normally in equation, when they will provide you with the material of the pipe, whether it is a glass or it's a rubber or copper or galvanized iron or stainless steel. Okay, let's say the material of the pipe is the stainless steel. Okay, stainless steel kat sini, and they will, from the table, from the Moody chart, okay, you will know what is the roughness of that material in millimeter. The unit is in millimeter. Okay, for stainless steel is 0.002 millimeter. Okay, 0.002 millimeter. And to find your relative roughness, sigma over D, this is sigma lah, roughness sigma. Okay, to find your relative roughness, you need to divide this by the diameter of the pipe. Okay, normally it will be given in the question lah, the diameter of the pipe. And let's say for example, we take the stainless steel pipe here is 1 meter. Okay, 1 meter. before you just divide this value, you need to change this millimeter in meter lah, of course. Okay, don't forget to change that in meter first before you divide with your diameter, because the given diameter is in meter. Okay, but if they provide the diameter in millimeter, okay, you can just simply divide lah the roughness with your diameter, and you will get your relative roughness, because this relative roughness is dimensionless. There's no unit for this relative roughness. Okay, so if you have both in millimeter, then that's fine, just use that. But if you get 1 in meter, so you need to change another one in term of meter lah. Okay, so when you get this value, you can plug in the equation, and you know your Reynolds number, so you can find your friction factor. But this way is quite complicated lah, because you need to play around with this equation. So that's why another two researcher named Hunter Rose and Lewis F. Moody, they try to simplify this equation. So in 1939, I think this is a quite interesting story. That's why I like to story here. And this Colebrook from the UK, a British researcher. So he introduced this equation first in 1939. Lama dah dia buat dia kaji, okay, dapatlah equation ni. But 2 years after that, 3 years after that, in 1942, Hunter Rose ni, dia adalah seorang American. Okay, he want to simplify this equation dalam bentuk gambar. As a common kalau kita tengok benda lagi pelajar engineering as you all, like me as well, we cannot see a lot of equation or a lot of words kan. Lagi senang untuk kita lukis sebab tu kita selalu dengar orang cakap boleh lukis tak lagi lukis lagi senang nak visualize lah. That's why he tried to draw a chart. Okay, this is his chart, the initial chart. He tried to draw to simplify this equation, but he couldn't manage to draw a full version of that chart. People still cannot use that chart, his chart, to get the friction factor. Okay, 2 years after that, Lewis F. Moody. So that's why we call this chart as Moody chart, even though it arises from Colebrook and from Rose. But because he finally get the real chart that people can refer in order to find the friction factor for a turbulent chart. Okay, for turbulent flow. Okay, so he improvised this chart, Rose chart, and he names his chart lah Moody chart. Okay, so that's the story lah why we came up with this Moody chart. This is Moody chart. Okay, so this chart will help us to find the friction factor, Darcy friction factor kat sini. Okay, there are 3 axes. Okay, one Darcy friction factor F that we want to calculate. The second axis is your Reynolds number, okay, where you calculate from the equation. There's another axis is the relative roughness. Okay, this is from your material, given the material, what is that? You can find out relative roughness divided by diameter of the pipe. Okay, so let's say in this chart, so they give you example how we can find the Darcy friction factor. Okay, let's say you calculate the Reynolds number, you get 300,000. So this is your Reynolds number, 300,000, and obviously it is more than 4,000. So your flow is in turbulent flow, So that's why we need to refer this Moody chart to get the friction factor. And then you have your Reynolds number, and let's say you have your relative roughness equal to 0.008. Apalah material apa pun, bila awak kira-kira awak dapat relative roughness equal relative roughness sigma over d. Okay, this relative roughness is equal to 0.008. Okay, what you do is that first from the Reynolds number axis, find your 300,000. Okay, and in this case kat sini lah dia bagi dalam 10 kuasa 3, 10 kuasa 4, 10 kuasa 5 kan. So 300,000 is kat sini lah 10 kuasa 5 3 kat sini. So this is 300,000. So you draw a line goes up. Okay, that's your one line. And when you your relative roughness is 0.008. So you refer your axis for relative roughness. Where is your 0.008? And it is here lah. Okay, this is 0.008. Okay, then you draw your another line from your relative roughness to the left. Okay, and intersect with your Reynolds number line. Okay, and this intersection, you keep on drawing your line to the F axis, the friction factor axis, to get to know your value for your Darcy friction factor. Kat sini berapa nilai dia kat sini dia tulis kat sini itu 0.035 Kalau this is 0.03 and this is 0.04, so this is 31, 32, this 0.04, 03 bagi ada 5 ni, so bagi 2 lah So 0.032, 34, 36, 38 and then 0.04. Okay, and your lines lies in between 0.036 and 0.034. So that's why it got here 0.035. Okay, so that's how you get your value for F, the Darcy friction factor, if you have your flow is turbulent. Okay, so you refer this chart lah. Alright, so that's how you get your F, and then you can substitute in your in this equation to find your head loss, the major loss. Okay, can you follow that? Any question? Boleh ke tak boleh?
Boleh sir.
Boleh Okay, if you don't get it, just ask lah Don't be shy or don't afraid. Okay, so that is major loss. Okay, the first loss in your piping system. And as I said earlier, we have another losses, what we call as minor losses. Okay, and we need to calculate that as well, because we want to know the total losses in the piping system. Okay, the major losses plus the minor losses, that will give you your total losses. Okay, and this minor losses is due to the piping system passes. Okay, the fitting, the valve, bands, elbows, everything lah, expansion, contraction, and this will give you the losses. Okay, and to find that losses, this minor losses, normally, okay, they will give you the loss coefficient of that losses lah. Okay, loss coefficient for valve, for elbows, for expansion, for contraction. So all of this has their own loss coefficient. Okay, loss coefficient for contraction berapa, loss coefficient for expansion berapa. So they have different value lah. So you need to sum all of that. Okay, if your pipe has few elbows, so you need to calculate the loss coefficient for the elbows. And if your pipe has expansion, so you have to add that losses as well to get your total minor losses. Okay, and to find that losses, you just use this equation. Okay, so minor losses HL again. Okay, if you want to differentiate with the minor losses, normally we write HL major, okay, and HL minor. Now, if you don't want to confuse lah with this term, both of them is the head losses, but one of them is major and another one is minor. Okay, so to calculate that for minor losses, we use this equation, the KL, the loss coefficient, times the velocity squared of the flow, divide by 2 times G. Okay, so this is the equation lah, the equation for minor losses, to get the minor losses. Okay, alright, so why this minor losses is generated in our pipe. Okay, give you for example lah, this apa semua ni. Okay, so let's say we look at this diagram for the pipe inlet. Okay, so pipe inlet you have this loss coefficient equal to 0.8. So this is pipe inlet and this is pipe outlet, pipe exit. Okay, if you can draw, so let's say we have reservoir and you have a pipe connected to the reservoir. So this is the pipe inlet, and if your pipe here connected to another reservoir, okay, so this is the pipe outlet lah. Okay, so this is outlet and this is inlet. Okay, so it will depends on how your connection with that reservoir and your pipe. So this connection will determine lah, will give you a different loss coefficient. If your loss coefficient higher, that means you have higher losses lah. Okay, if you have the loss coefficient a smaller number, that means your losses is small. Okay, let's say for example these three different inlet. Okay, why we have this higher and this smaller and this smaller? Because of this connection. You can imagine if you have a flow inside this reservoir. Okay, and this flow try to get into the to the pipe inlet, because you have this kan, ada macam ni ada the entrance tu dia connected macam ni. So this flow will have losses lah, dia tak akan masuk kan, sebab ada benda ni yang menghalang dia kan. So let's say dia have flow here and kat sini, so this flow will collide with this wall and will not get into the pipe inlet. Okay, so that's why you have the losses, and that losses is high lah, 0.8. Compared to this connection without the this macam ni kan, without I'm not sure what we call this. Okay, without that entrance, straight away to the entrance, so you reduce that yang loss dekat sini ni so all the flow we try to get into the pipe inlet kan. Okay, but because this is a 90 degree bend, so might as well they have the susah jugalah nak masuk dia akan langgar-langgar sikit kan, so this will create a losses. Okay, so that's why your loss coefficient reduce from 0.8 to 0.5. Okay, but if you can improve this using a well-rounded connection macam ni ada smooth connection kan, so your fluid can flow into the pipe inlet smoothly lah, smoother compared to this sharp edge. Okay, and because you have this smoother flow comes into your pipe inlet, you reduce your loss coefficient, that's why it's 0.03. You makin kurangkan loss coefficient of the pipe inlet. Okay, so that's how you have a different loss coefficient for different types of pipe inlet lah. Alright, and for pipe exit, and because the flow from the pipe to the reservoir, okay, you will see that these three exit have a similar loss coefficient. Because we don't have kat entrance ni dia ada banyak langgar-langgar lah kan, dia akan ada susah nak masuk so that's why you have different loss coefficient. But for exit coefficient, it's just the same, because it's just the fluid is flowing to the reservoir so just semua akan keluar. So regardless of this well-rounded or sharp edge or whatever, you will still have the same loss coefficient alpha here. Okay, so that is your loss coefficient for exit. Okay, similarly if you have expansion, okay, expansion means your two pipes is connected with a different diameter. One with smaller diameter, this is the first pipe, and then the pipe is this one with this with the larger diameter. So when the fluid flow, okay, it will create like this, akan ada flow yang macam ni, and this will create a losses. Okay, so that's why you have the expansion losses lah. Okay, and these losses we calculate with this bigger pipe. Okay, we will use the this pipe lah. And for contraction, opposite for this one, your flow is come from your bigger pipe try to get into the smaller pipe, and as this diagram shows you, you will have these losses, akan ada losses yang tak akan masuk tu. Okay, that's why you have this loss coefficient for contraction. Contraction maksudnya dari besar ke kecil. Okay, so that's the explanation lah why we have that minor losses through the fittings, through the valve, through the elbows, through the yang lain-lain lagi lah. So this is through the bend. Okay, if you have a 90-degree smooth bend, so this is your loss coefficient 0.3. But if you have a 90-degree meter bend, not a smooth bend, so your loss coefficient is higher. You will create more losses because your bend is not smooth compared to this one. Okay, but if you put a vane, okay, this vane will help the flow to flow. Dia can help lah the flow to ambil corner kan, dia ke corner macam ni kan. So that will help the fluid to goes down. So that's why your loss coefficient reduced to 0.2. Okay, so that's different coefficient depends lah on your types of this bend. And 45 degrees, so you have another loss coefficient. Okay, and this 180 written bend, okay, ada loss coefficient there. The T, the junction, ada loss coefficient. The T for line flow ada coefficient, loss coefficient. Also the threaded union pun ada loss coefficient. Okay, sama juga dengan valve pun ada loss coefficient. Okay, if you have a valve, so that valve will have a loss coefficient because the fluid flow through the valve, so it will create losses lah. Okay, and that losses will depend lah how much your valve is closed. Okay, if closed fully, that means there's no flow can pass the valve kan. But if you like quarter close, maksudnya you buka sikit, so you have loss coefficient 0.2. If you close half, maksudnya lagi banyak yang awak block, so you have a lot of losses. So you will have a higher loss coefficient. And if you third quarter close, maksudnya banyak lagi yang ditutup, flow tak boleh lalu, so you create much more losses. Okay, that's why your loss coefficient is higher. Okay, that's a valve, valve loss coefficient. So that's the minor losses, and you can calculate using this equation. Just put the loss coefficient given in the question or in the example times the velocity squared over 2g. Okay, after you calculate that minor losses, and as I have mentioned earlier, the total losses is the measure and from the friction, okay, that you have calculate plus the minor, that will give you the total loss of the head loss. Okay, and this is the equation lah. If you have a different pipe, so you need to calculate for each pipe. Okay, if you have only one pipe, you can just simply use okay, the equation. If you have one pipe with a constant diameter, that means your velocity across that pipe is constant. So that's why you don't need to calculate one by one. Okay, that's why you have this equation. But if you have two different pipes with different diameter, so you need to calculate each one of them lah. Because the velocity inside that pipe will be different kan. We know from the continuity equation, the velocity will be different according to the area kan, the area of that pipe, the cross sectional area. Okay, so you have a different diameter, that will give you a different area, and this will give you a different velocity. So that's you need to calculate each losses in each pipe, pipe, bigger pipe and smaller pipe. Okay, so that is total head loss. Okay, any question before I show you some of the example? Ada soalan nak tanya? Tak ada. Senyap ni semua ni?
Tak ada, sir.
Okay. Alright, so I show you one or two example and how we can calculate these losses. Okay, so this is one example. Water at 5 degree with rho of 1000 kilogram per meter cube, the density, and the dynamic viscosity mu 1.519 times 10 to the power minus 3 is flowing steadily through 0.3 centimeter diameter of 9 meter long, and the length is 9 meter. Okay, the diameter is 0.3 cm. At an average velocity of 0.9 meter per second. So this is V, average velocity. So determine the head loss. So this is your major loss, and the pressure drop. Okay, head loss ni total lah, total minor losses and major losses and minor losses. But because of this pipe don't have any piping system yang lain, tak ada connection, tak ada apa, so there is no minor losses lah. It's only major losses due to the friction. And they ask you to calculate the pressure drop as well. Okay, this is head loss, the HL, and the pressure drop, okay, delta PL. Okay, and the pumping power requirement. Okay, they ask you to find the pumping power requirement to overcome this pressure drop. Okay, first thing first, we need to know whether our flow is the turbulent or laminar. So to get that, we use this equation, Reynolds number. Okay, rho times velocity average times diameter over mu. So we have everything. We have the rho, we have the velocity, and we have the diameter. So you need to change the diameter in terms of meter. This is 0.3 cm. Okay, you need to change this in meter. Divide by dynamic viscosity. They give you the dynamic viscosity. And then you can get your Reynolds number, and in this case Reynolds number is 1777. Okay, because this is below than 2300. Okay, so our flow is flowing with a laminar condition. Okay, laminar condition lah. Okay, so that's the first thing. That's why we learn how to calculate the Reynolds number. Okay, so after we know that this is laminar flow, we can simply use this equation lah to get the friction factor. We don't have to use the Moody chart because this is laminar flow. Okay, so just simply 64 over Reynolds number will give you the friction factor, the Darcy friction factor. You get this friction factor because we want to find the head loss, kan? The head loss equation require us to find the F. Okay, this F. Okay, that's why we find the F. Okay, when we get the F, we can simply put again in this equation. We have the L 9 meter, we have the V 0.9, we have the D 0.003, and we have the G lah. Okay, so that's why we find the F. Okay, plug in everything, the value inside this equation, you will get the head loss is 4.46 meter. Okay, this is your answer for part A, the head loss. Okay, now they ask you to find the pressure drop. Okay, next slide. The pressure drop is equal to this equation. Okay, FL over D times rho V squared over 2, and you can plug in everything, you will get the answer. Or the much simpler way is, apa the much simpler way to get the delta P if you don't want to use this equation? Macam mana cari delta P, pressure drop? Anyone want to try? Tak ada? Siapa nak try tak? Macam ni nak, without using this equation, you can find your delta PL.
Yang P1 minus P2 je.
Itu kalau ada value P1 dengan P2 lah. Ni awak tak ada value tu kan? Using the HL, what we do with the HL?
Bahagi rho G.
Bahagi rho G or times rho G? Times kan? Because we know that P equal to rho GH rho GHL kan? Okay, so you already calculate the HL here 4.46 meter, and they ask you to find the delta P L. Okay, so that's why to get delta P is just multiply the HL with rho G lah. Okay, if you want to double check this, okay, we can check this. Okay, H, the 4.46 times rho times G, you will get the same value with this one, 43.7 kilopascal. 4.46 times 1000 times 9.81. Okay, so this will equal to this value lah. Okay, so you can use this equation, or you can just simply times rho G lah, because we know delta PL over rho G will equal to HL n. Okay, that's settled for number 2. And we know the losses already, the head loss. We can find the pumping power requirement by using this equation. Okay, so this is Q. I forgot to change, because we use term for Q for volume flow rate. Okay, that's why we use Q. I change this Q. Okay, the Q equal to the area times velocity. So you have this this value for velocity and also the area. So you can find your Q. Okay, and when you get your Q, you can just simply times Q with delta P to get your pumping power requirement. Okay, or you want to use another equation using the head loss pun boleh. Okay, but that's time with the mass flow rate lah. Mass flow rate times G times HL kan. So that will give you the same. Okay, or you can use this equation as well, where you find the delta P. Okay, so this will give you 0.28 watt. Okay, and this is the watt the pumping power requirement needs to be put inside our pipe in order to recover back the head losses. This 4.46 meter losses. Okay, alright, itu contoh yang paling mudah lah, because it's just a laminar flow. You don't need to refer your Modi chart. You don't have any minor losses. Okay, so we can see another example where we have started before. Okay, this one. Okay, yesterday we have already calculate the Reynolds number for this problem and the water supply system for this this diagram, and the water supply through the pump. That's why you have a pump to add and then additional force to flow the fluid. Okay, so you have everything, and you have already calculated yesterday. You get 64,809, and this is turbulent. Okay, so we can answer the B question, the friction head loss in pipe, which is the major loss lah. The friction ni due to the major loss is due to the friction. This is your major loss. Okay, you find your major loss. Okay, so how to calculate this major loss? We use the equation. Okay, HL, okay, sama dengan F L D V squared over 2G kan. Okay, and you have everything. You have L, you have D, you have V, you have dah calculate semalam, you have G, but we don't have the F. Okay, to get the F, because this is turbulent, so we will refer to the Modi chart. Okay, from the Modi chart. Okay, so your Reynolds number is 64,809. Okay, so we go to Modi chart. Mana Modi chart ni? Okay, so our Reynolds number is 64,809. Okay, so this will be 1, 2, 3, 4. Okay, so 6.5 lah. 6.5 to the power of 10 times 4 kan. So you go to your 10 times 4 as ni. Okay, and it is 6.5. 6.5. So your line is here lah. So this is 6, 7, 8. So it's in between. So this is 6.5. Okay, so you draw your line up. Okay, And you need another as this is the relative roughness. Okay, from our question, it is a galvanized iron pipe. Kan? They mention here, it is a galvanized iron pipe, and the diameter is 0.15. Okay, so we go back to the Modi chart. Okay, and find the galvanized iron, which is this. Okay, galvanized iron has a 0.15 millimeter roughness. Okay, and to get your relative roughness is 0.15, because this is in millimeter, so you need to find to change that in millimeter. Divide by 1000, divide by your diameter of the pipe, which is 0.15. Can? Okay, the diameter of the pipe is 0.15, 0.15 meter. That's why you divide by your D to get your relative roughness. Kat sini. Okay, so you calculate this value, and you will get your value for relative roughness is equal to 0.001. Okay, and you find your this value from your axis for relative roughness. It is here. This is 0.001. Okay, so you draw your line. Okay, from this 0.01 to the left. Okay, sorry, tak apa nak straight. Okay, and intersect with your Reynolds number, and keep on your line until you get your Darcy friction factor here. Okay, so whatever value here that you have, you get. Okay, when I do this properly, I get 0.023. 0.023. You can double check this if you draw a line properly. Okay, but this is how you do this. You will get 0.023, your F. And then go back to the question. Okay, so you already get your F, so you can plug in the value inside this equation, and 0.023 times the length of the pipe, which is 60 meter, divide by the diameter 0.15 times the velocity squared. You already find it, 0.566 squared over 2 times G. Now you will get the value for your major loss is equal to 0.15 meter. Okay, so that is your friction head loss, because of the major loss lah. Okay, friction ni major loss. And then the C, they ask you to find the minor head loss. Okay, the minor head loss is equal to KL, loss coefficient, times V squared over 2GN. Okay, so that's why they give you in this question the loss coefficient for pipe entry 0.5, and this is 1 kat sini the pipe entry. Okay, and the pipe exit kat sini, this pipe exit. Okay, because the flow is flowing macam ni kan, dia akan dari bawah, dari atas, ke kanan, ke atas, ke kanan. So this is your pipe exit. So they give you the loss coefficient for that. And you have the globe valve, 3 globe valve, 1, 2, and 3 globe valve. So this valve has their loss coefficient as well, 1.9. And you have a check valve here. This is a check valve, and this have another loss coefficient 3.0. And you have a bend, 90-degree bend, 1, 2, and 3. Okay, so this bend also has a loss coefficient, and they give you the loss coefficient number is 3. Okay, so you need to add all of this loss coefficient. Okay, I write it here. Okay, first the entry coefficient 0.5 and only 1, so that's why you times 1. Okay, plus the exit also 1. Okay, so 1 the loss coefficient times 1 exit. And the globe valve you have 3, 1, 2, 3, so plus the loss coefficient of globe valve is 1.9 So times 3, because you have 3. Okay. Plus, you have the check valve, one check valve, with the loss coefficient of 3. So 3 times 1. Okay. And lastly, you have exit 90 degree bend. Okay. You have 3 90 degree bend. Okay. So the loss coefficient also 3. So 3 times 3. Okay. So you add all of this loss times the V squared is 0.566, okay, times V squared over 2G, okay, and this should give you the minor losses, which is 0.313 meter, okay. So add both the head friction head loss with your minor loss, so this will give you the total head loss lah. Okay, the total head loss will be equal to 0.63 okay, so that is your total head loss if they ask you. In this case they don't ask you, kan? Okay, but you can use you need to know this total head loss, because you need to find the required pumping power. Okay, so you can calculate this, okay, using the equation before tadi, NW equal to Q times P, kan, the pressure loss. Okay, so you that's how you calculate this required pumping power lah. Okay, alright. Any question so far? Ada soalan?
Oh, sir.
Ha? Tak ada?
No
soalan. Okay. So I hope you understand, because you don't have any question. So I assume you understand how to calculate these losses in the piping system. Okay, I repeat back. So there are two losses, okay, in the piping system. The major losses, what is this? Okay, yeah. So losses, there are two. One major due to your friction, and another one is a minor due to the fittings. Okay, so you need to add both of these to get your total head loss, okay, in your piping system. Right? Okay, so that's it for today. Okay, we have one more subchapter, two more subchapter, which is the piping network and also the steady flow incompressible energy equation. Okay, so this will we will cover this next week. All right, because this related. Okay, I don't want to cover this today. Okay, I think this is enough for you. Okay, so we'll continue our lecture and tutorial next week for that subchapter, and we can wrap up lah all this chapter 4. And the ada dua kelas kan, next week ada dua kelas. So the first class I will finish the theory of that piping network and this energy equation, and another class we will do the more questions, more tutorial on this chapter lah. We do it together. Alright. Okay, that's all for today. Okay, I think we can end our class earlier. And yeah, we have long weekend this week. Okay, I wish you happy holiday if you are going somewhere or just stay at campus. Okay, and we shall meet again next week on next Wednesday. Next Wednesday we meet again. So thank you for your attendance. Right, and Assalamualaikum warahmatullahi wabarakatuh.
Thank you, sir.
Waalaikumsalam. Thank you, sir.
Thank you, sir.
Waalaikumsalam. Thank you, sir.
Yes, sir.
Okay, sir.